Okay, so yeah, off we go. Okay, so topographical maps are just a bunch of level sets, right? Okay. So here's a neat fact. A little surprising. I mean, I've gone to some trouble to make sure we distinguish in our minds between level sets and graphs. They're very much different things, right? But it turns out they're connected geometrically. So here's how that works. Notice that what I've written down here is a graph, right? That's a graph of this function called f. And I can take that graph and I can talk about doing a horizontal cross-section of that graph. And if you think about it, a horizontal slice, well, that's I'm intersecting with a plane, right? A horizontal slice means we're intersecting with this horizontal plane, z equals some constant. And altogether, if f is z and z is c, then you kind of connect the dots, and f is c, which is exactly what we would have gotten if we had been talking about a level set of that function. So this is the nice pithy little summary. Level sets are horizontal cross sections of graphs. It just works out that way. So here's a nice example. We're going to look at this function right here. And on the one hand, here's what a level set of that function looks like. Again, you set the function equal to various constants. You get these circles. Okay, let's see here. And now, same function. Let's talk about what its graph looks like. Keep in mind the rule, if you want to talk about a graph of a function, you set the value equal to a new variable. In this case, I'm using z. What this graph looks like, I'm going to just assert what it is, and I will demonstrate that I'm right in a few minutes. We'll get to it. But I claim, as will be justified later, that this is kind of a bowl sort of a thing. And now, while we're here, let's take a moment to doff the cap and recognize that these are really different, right? The level sets are a bunch of circles in the plane. The graph is a kind of a bowl-shaped surface in space. Totally different pictures. Okay, granted. But then check it out. If I take cross sections with these horizontal planes, setting z equal to constant, right? And think about what do those look like, which again, as previously noted, that gives me these circles, right? You get x squared plus y squared equals constant, exact same as these circles. And one little asterisk, and this is annoying, but yeah, okay, technically these circles are suspended in three-dimensional space. These circles are sitting in the two-dimensional plane. Yeah, they're different in that sense, but when I say they're exactly the same, what I mean is if you look at the x and y coordinates only of these circles, these cross-sections, they're exactly the same as the x and y coordinates of these circles in looking at x and y only. So, neat fact, there's a connection between those two things. Now, here's a really important point. Here's why I've been making such a big deal about all this business about graphs and level sets and the differences between them. When you're looking at a curve or a surface, and you want to understand it as on the one hand being a level set or on the one hand being a graph of a function, the question comes up, okay, well, yeah, but which function? And there are different functions that you can relate to a given geometric object. So, for example, and this is a nice little example here, let's look at this line with this equation right here. Right, perfectly reasonable little line there. And I claim that this line is the graph of that function. I claim it's a level set of that function, and I claim it's parameterized by that function. So there are three very different functions. Check out how very different those functions are. They don't even have the same number of input variables. They certainly don't have the same domain and target. Right? These are really different functions. They all describe the same line, but in different ways. Right? Level set of one, graph of another one, parameterized by the third one. So what y'all are going to notice, and we haven't gotten into this yet, we'll be just barely getting started on derivatives later today, just a few minutes, is that when we write down various objects of calculus, and then we ask the question, what do they look like? We're going to get different answers for different kinds of constructions. So we're going to develop, therefore, kind of what I like to call a calculus of graphs. And then we're going to have a completely different calculus of level sets. And we're going to have a completely different calculus of parameterizations. Completely different geometric interpretations depending on which kind of construction you're looking at. So back to this example, why do I have to keep it straight? Which function relates to this curve in which way? Well, because if you apply the calculus of graphs to this function whose graph isn't what we're interested in, then you're going to get a bunch of nonsensical garbage answers. And I've seen this happen a million times. It used to happen really commonly when I first started teaching this course long ago. The more let's see how to say this. I started emphasizing these points and these distinctions more and more. And so the occurrence of these kinds of confusions and catastrophes has become less and less over time. But we're not at zero yet. There is still a problem with students just kind of playing a little too fast and loose and maybe applying the calculus of level sets to the parameterization and getting nonsensical garbage results. Okay, so please be very, very careful. If you want to apply the calculus of graphs, you've got to figure out how to view your line as being a graph. Namely, you've got to find specifically that function. And if you want to apply the calculus of level sets to understand this line, well, you've got to apply it to this function, not that, not this. Right? So let's talk real quick about how to find these functions. The parameterizations we've already spent a bunch of time talking about. You all know how to parameterize. We'll go over that again. Let's see here. Let me first convince you, wrong color. Let me first convince you that a level set of G is this line. And the way I'm going to do it is point out, well, this is what level sets look like. And now question, can I come up with a value of C that makes this equation equivalent to that equation? Well, yeah, sure, no problem. Obviously, C equals 6, nothing to it. So going the other way, when you have the equation of a line, how would I view that as being a level set? Notice, all I would need is to figure out how to turn this equation into something where I have nothing but a constant on one side. Conveniently, this came to me with nothing but a constant on the right side. Well, sometimes you might have to move subtract some terms over to the other side, whatever, right? But just do whatever you got to do to get where the non-constant terms are on one side, and then you'll have equals constant, and then bam, whatever's on the left is your function, and whatever's on the right tells you which level set you're looking at. So that part's pretty straightforward. How do we find this function? There's an analogous process. First, let me persuade you what the graph of this function is. The graph I get by setting the value of the function equal to a new variable. Let's see, all of this is written in terms of only x, so I'm allowed to say I'm going to have my new variable be y. So this is the equation of the graph of f, and you can persuade yourself without too much trouble that that equation is equivalent to the dark blue equation right there. And it is, tossing terms around, no big deal. Okay, so again, how do you go the other way? How do you take this equation and view it as being a graph of something? Note, taking an equation and putting it into a form where it is a graph just means I need to have solved for one of the variables. So take your equation like this, just pick a variable that you can solve for and solve for it. Boom. Now you found the function whose graph is your original equation. All right, so that's how that works. Okay, we will see more of this stuff as we go along. By the way, I should point out, just for your consideration, this example is one of my favorite examples. A metric of how much I like this example is how many times questions like this have showed up on my old midterm exams. So you can actually count them up, and it's quite a few. So you look back to my old exams, there's a bunch of these. And when you see those old questions, keep in mind, I know that the actual mechanics of the algebra is not hard here, right? The point here is interpreting the question accurately, using terminology accurately, right? If the question asks you to provide a function, you got to give me a function, right? You can't give me an equation, right? So anyway, the delicacy to how it's written down, this is where most students' downfall is. Most students don't get in trouble because they don't know how to solve for y. That's trivial. That's high school algebra. That's not what the question's about, right? So make sure that you focus on the proper, strict interpretation of the terminology and the delicate application of the ideas. Yeah.
Could you please do the parameter?
Yeah, no, so this is, we talked about this back in chapter 1, so I'm just going to refer you back to that. So yeah, we spent some class time on that already. But so keep in mind, one of the luxuries of this class is you can just look back at those old recordings and it's all there. Yeah. All right. Okay, so here's a neat fact. This is another one of these things where the algebra is actually pretty easy, but this is about the careful interpretation that comes up with a nice result. So let's start by looking at this algebra right here in the box. And notice that hardly anything happened. This is a total yawn. These two equations are obviously equivalent. All I did is I took what was on the right and I subtracted it over to the left. Right? Nothing of significance happened there. Okay. True. So these two equations describe some hypersurface. I'm just going to call it S, whatever. It's the set of solutions to those equations. Fine, whatever. Okay, notice though, this first version has that written as being a graph. Let me do it like that. Specifically, it has my surface written as a graph of this function called f that has n input variables, whatever that expression might happen to be. Okay. On the other hand, this equation at the bottom is written, you can see right here, it's written as a level set. It's written specifically as a level set of now this expression, which is a different function. Very, well, I mean, you might say subtly, right? But noticeably different function. This formula is not the same as the formula for f. Right? So the really awesome punchline here is that whenever you have a graph, any graph at all, interpreting strictly what we mean by the word graph, right? If you have a graph of some function, you can do this little trivial little algebraic move and reinterpret it as being a level set of a different function. Now, why would we ever want to do such a thing? The answer is sometimes, while a surface might come to us as a graph, we might want to be able to apply the calculus of level sets. The calculus of level sets is pretty awesome. There's some cool stuff in there, and that's a neat tool, and we might want to be able to use that tool. But if the surface comes to us as a graph, then in this form, I cannot use the calculus of level sets. It's not written as a level set of something. It's written as a graph of something. right? So this one little triviality, and again, major yawn, boring, hardly anything happened except that now I get to say, hey, I'm looking at a level set of this other function. And I can apply the calculus of level sets to this other function and get what I need to do. So here's a nice little example. We start by being interested in the graph of this function, x squared plus y squared. And so again, there's the function. And here's me taking the graph of it. Right? So this equation represents the graph. And if I wanted to apply the calculus of level sets to this surface, by the way, there's a paraboloid. Oh, wait a second. No, I'm sorry. We haven't got ahead of myself there. Yes, question.
Can you go back to the previous slide really quick?
Yeah. Yep. Is that good?
Yes.
Okay, yeah, cool. So if I wanted to be able to apply the calculus of level sets to this thing that's not written as a level set, I absolutely cannot do the calculus of level sets to this function because I'm not looking at a level set of that function. But I do the little fast one, right? Pull a little quickie there. Trivial, yawn, boring, hardly seems like anything happened, but it's now a level set. It is a level set specifically of this function, and this original surface in green that I was interested in, I can understand it by applying the calculus of level sets to this G. With this formula right here, I can apply the calculus of level sets to that function, and it's all good. Really neat little trick. Again, subtle, delicate, but ultimately very powerful. Okay. So, bad news, it doesn't go the other way. While every graph indeed is a level set, not every level set is a graph. Easy counterexample, here's an equation that is a level set. You can see right there, right? It's the level set, the one level set of this function. And it's easy to understand what that level set looks like. It's that circle. And is this a graph? Nope. Fails a vertical line test. Crash and burn. We lose. It's not a graph of anything. Yes?
Why is it inverse? Like, why is it G inverse?
Oh, that's just a notational thing? Yeah, no, I hear you. That's a notation. If you look back at the definition of level sets, the idea is that there are certain values of x and y that when you put into the function will give certain outputs. And we're looking to fix an output, namely 1, and kind of reverse engineer what are the corresponding x's and y's. And so it's like we're going backwards through the function. It's a pre-image, is the point. So yeah, so that's just a notational thing. To be clear here, by the way, this function g is definitely not invertible, right? So when I write g inverse, I'm not saying the inverse function. This is just a notational, it's a kind of a math slang. It's not real. Yeah.
So it's just the pre-image of when x squared plus y squared equals 1?
Yeah.
And that's just the notation for when the level set is going to equal 1?
This is a notation to represent the level set itself. This represents all solutions to that equation, a.k.a. it represents this circle.
Okay.
Yeah, totally. Yes?
Yeah, so now that's the level set, like x squared plus y squared equals 1 because we have a constant of that.
Yes, that's right.
It's not a graph to be concealed in that.
Exactly.
Okay.
Yep. Yes.
I had a similar question.
Oh, okay. So you're good? Okay, cool. Okay, so enough with functions and such. Now we're going to look at equations. So we're going to look at equations of 3 variables. Y'all know how to deal with equations of 2 variables, to some extent. By the way, let's make a quick observation about what y'all know about how to understand equations of 2 variables. You know certain tips and tricks. Right? You do not know how to identify every possible equation involving 2 variables. There's too many of them. They get too hairy and nasty, and you couldn't possibly. Right? So you have a limited set of tools that apply, surprisingly often, and that's just the best we can do. Okay. So the same thing is going to be the case here. So when you're looking at equations of 3 variables, we're going to be talking about surfaces in space. And I'm going to show you certain tricks, right? Certain tools for your toolbox, but don't get it in your head that we're going to necessarily be able to understand every single possible surface, every single possible equation of three variables. We can't. There's too many. It's too weird. Right? So just a couple of tips and tricks. And here we go. So the first one is about rotations. This is a lovely point. This is underappreciated. It's undersold. This is one of my favorite observations in this area. If a certain condition happens, it turns out that your surface is rotationally symmetric. That's a powerful geometric conclusion that we get, and we get to draw that conclusion at the expense of simply observing this one condition up here. And the condition, just to be explicit, the condition is that in the equation, x's and y's can appear only as part of this expression. Square root of x squared plus y squared. So as long as the equation has the feature that x and y appear only in that form, there's no sine x anywhere in the equation. There's no e to the x plus y anywhere in the equation. If x and y appear only in that form, then it's rotationally symmetric. Powerful geometric conclusion. So now before I show you how to use that, let me show you why it's true. This is just kind of an observation, but I'm going to take a point here, some arbitrary point. Let's think about what would happen if I rotated that point around the z-axis. Right? You get a bunch of other points, such as this point right there, let's say. So one is the rotation of the other. Let's think about those 2 points. They're different points. They have different coordinates. You're going to be plugging in different numbers into your equation, whatever your equation is. But even though they are different points, they have the same distance to the z-axis because of the fact that the one is the rotation of the other. Same distance from the z-axis. That distance is this square root of x squared plus y squared. That means that even though purple and dark blue have different x and different y, they have the same value of this expression. That's the only way that x and y even show up in the equation in the first place. So who cares if they have different x and different y? Those differences between the x's and the y's are going to disappear as soon as you plug into this expression. Right? It's just kind of a slick observation. Give me 2 seconds. Of course, they also, again, because they're rotations, they also have the same z. And so when you plug these 2 different points into whatever your equation is, you're effectively plugging in all the same numbers, and so either they both work or they both fail. Yeah, question?
Can you define exactly what you mean by rotationally symmetric?
Yeah, that's right. So a surface is rotationally symmetric if when you rotate it, it doesn't change. It remains the same surface. Or you could say that differently as if you have one point on the surface, then when you take that point and rotate it around by any amount, that the resulting point will also be on the surface. Yeah. Is that cool?
Yes.
Yeah. Okay, so it's a pretty cool fact. And again, it's just about the geometry of rotations. When you rotate, you don't change square root of x squared plus y squared, and you don't change z. And so equations that have this property are going to have the feature that these points are either both on or both not on, and again, therefore, rotational symmetry. Now, a different way to see this, if you like, suit yourself, is that if you take one of these equations and convert to cylindrical coordinates, right, this is just going to turn into r, which has no thetas in it. And there are no other x's and y's. So, and then the z stays z. And so when you convert an equation of this sort into cylindrical coordinates, there just won't be any thetas. And if there's no thetas, then it's rotationally symmetric, as we've argued before. So take your pick. These are 2 nice little arguments, both of them. I like them about equally. Okay, next key observation. When a surface is rotationally symmetric, Right? So it's as you rotate around the z-axis, it never changes. It's always the same thing. Then it is a rotation. Now this is a purely geometric appeal. You just got to think about what is this? What do these things look like, right? If a surface is rotationally symmetric, you can pick any cross section and just rotate that cross section, and it will generate the whole surface. You got to think about that geometry. Feel free to come talk to me after class if you want me to draw some pictures and make a case for that, but it's just a geometric appeal. So with that noted, here's how we can actually get some stuff done. So let's look at this surface right here. We've talked about this surface in the past, and I made an assertion, trust me, assertion that this is kind of a bowl. And I gave you no justification for that other than maybe you trust me, right? So, okay, let me try to persuade you mathematically that this is in fact a bowl. Step 1. X and Y appear only in the special form, and therefore it's rotationally symmetric. Now, you may quibble and say, I don't see the square root in there, and okay, that's fair. So let me rewrite this as square root of x squared plus y squared quantity squared, and there you go. X and Y appear only in the special form. And by the way, just as a side note, this form and that, these are they're exactly the same expressions, right? And so if you have to rewrite it a little bit, as long as it's truly equivalent, totally fine, right? It doesn't have to be visibly written in that form, but it has to be equivalent to that form. Yeah.
In this case, is z a constant?
No. Z is x squared plus y squared.
Oh, yes, it's a constant.
Yeah. So our equation is like this, and so z. So the bigger x and y are, then the bigger z is. Yeah.
So it's like f of x, y.
Yep. That's right. So this is the graph of x squared plus y squared. That's right. Okay, so we've just observed x and y appear only in the special form. This thing is rotationally symmetric around the z-axis. That means that it is a rotation of its cross-section. I can pick any cross-section that I want. Now, I'm going to arbitrarily pick the YZ plane just because, no particular reason. But just to be clear, if I wanted to pick the XZ plane, I could do that. Or if I wanted to, for whatever sick reason, if I wanted to pick some angled plane like that, it's all good, right? Pick any plane you want that contains the Z-axis. It's got to contain the whole Z-axis. And I figure, let's pick the easiest ones that we can. In this case, I'm going to pick the YZ plane. Yeah.
Wait, I wanted to ask how you made that, how you chose. Is there a particular way of thinking?
How I chose this particular plane?
Yeah.
Oh, arbitrary.
Okay.
Doesn't matter. I like it because when I look at it, I'm looking straight at it, right? And because I like coordinate planes because they have easy equations. Pure laziness.
Okay.
Yeah. Right. Okay, so now let's think, how am I going to find the cross-section of this surface in this plane? And that's actually pretty straight. There's the equation of that plane, and I plug it in. And then I get this equation, z equals y squared. And that's very familiar. All right, that's just a parabola. That's high school algebra. Y'all all good with parabolas, I'm sure. Okay, so again, stepping back, quick pause. What do I know? My surface is rotationally symmetric, and therefore a rotation. This is what one of its cross sections looks like. So altogether, my surface is whatever I get when I rotate this parabola around the z-axis. Geometric appeal, when you take that parabola and rotate around the z-axis, you get a kind of a bowl, kind of like that. And by the way, this is called a paraboloid. That's just a terminology. But there you go. Yep.
Does the vertical line test fall apart in 3D? Because you said that a circle's not a graph, but this is a graph.
No, the vertical line test works just fine. Yeah. So so in general, if you want to view, if you have some surface, not a curve, right? If you have a surface and you want to know if the surface is the graph of some function, specifically if you want z to be a function of x and y, vertical line test.
Okay.
Yeah, totally. Yeah. Okay, so there you go, done. And I think this is a lovely argument. We turned a hard problem into an easy problem effectively by this rotation and cross-section argument. We turned a question about an equation of 3 variables into kind of a flashback question about an equation of 2 variables where we already knew the answer. All right, let's see another example. So here's an equation. You'll notice x and y appear only in the special form. No other x's, no other y's. Sweet. So rotationally symmetric around the z-axis, which means it is a rotation of its cross-sections. I can pick any cross-section I want, right? Well, yeah, question.
Quick question. So you say that we have x and y appearing in the special form. So even if we have z right next to it, it's still...
Yeah. The z is allowed to do whatever it wants, right? But it just has to be the case that x and y can appear only as part of x squared plus y squared or square root of x squared plus y squared. Take your pick. Yeah, right. Yep. Yeah. Okay, we get to pick any cross-section we want. Now, just to show that we can, here I'm not going to use the YZ plane like I did last time. Here I'm going to use the XZ plane. What does that buy me? Nothing. Just show it off, right? Flexibility, showing that you got options, right? Pick any plane you want. So, okay, here we're going to pick the XZ plane. There's the equation. We plug it in. And that means our cross-section is this, which is a hyperbola. Flashbacks to high school, Algebra 2, right? I'll bet you half of you at least have kind of forgotten what the deal was with hyperbolas, right? It's okay. Make sure to brush up on that. It's it's annoying, but we do have to be good on all that stuff. So you don't have to worry about foci and asymptotes and stuff like that, but you need to be able to make a rough sketch of what your hyperbola looks like, and in this case that hyperbola looks like this. If you're a little rusty on that, if you're like, I always get confused which way it goes, does it go this way or that way, come talk to me in office hours. I'll be very happy to help you out with that. I have a little system that I use that doesn't require me to remember any facts. All it requires is for me to think through a certain little analysis. And I've been using the same trick for the last 30 years. So I think I'm good with it. Anyway, I'll show you my trick if you're interested. Come on by. Okay, so hyperbola. That's the cross-section. Our surface is what you get when you rotate around our axis, namely the z-axis. Geometric appeal. And you just got to think about the geometry. Think about that orange cross-section curve. When you rotate that around, I claim you get something that looks kind of like this. Approximately. It's poor art, but you get the general idea. And this is called a hyperboloid. They say of one sheet because it comes in one chunk, and there's another kind of hyperboloid we're going to see in a second that has 2 sheets. Okay. Look back at this argument here. This is specifically about x and y appearing only in the special form, and then the result being that the rotation is around the z-axis. Challenge question for y'all to think about on your own at some point. How would you adapt this argument to equations that would have symmetries around the y-axis or the x-axis? And here's the good news. It's exactly what you would think. The argument goes through exactly analogously. There's details to be thought through. There's pictures to be redrawn. There's steps to be rechecked, right? But everything goes through exactly like you would hope, and I want to strongly encourage y'all to think through both of those arguments. But question?
Yeah, quick question. You said that you can have situations where it's not just symmetrical along like the z-axis. So in that case, you still require x and y to be...
No. So that's why I'm saying you got to kind of rethink the whole thing, right? So whichever axis you want to conclude a rotation around, it's the other two variables that have to appear only in the special form.
Okay.
Yeah. Right. So think through those details and draw those pictures and redo the reasoning. Here's an example of that in use. Let's look at this equation. Are x and y only in the special form here? And no. That minus sign is super annoying. It just messes the whole thing up. X and y, there's no way I can rewrite this so that x and y appear strictly only in the special form, losing. But I can rewrite it like this, where y and z appear only in the special form. So this is rotationally symmetric around the x-axis. It's not rotationally symmetric around the z-axis. It is around the x-axis. Okay, so now where you go from here, again, is kind of, you got your options. Pick any plane you like that contains the x-axis. Doesn't matter. Whatever you prefer. I'm going to pick this one for no particular reason. And you put it in there and you see what happens. And that resulting cross-section is this hyperbola, which looks like that. Again, flashback to high school algebra. Make sure you're good with that. Come to office hours if you want me to remind you how to figure which way it goes. And so we have a rotationally symmetric surface. This is its cross-section. Therefore, I have to take this orange curve and rotate that around the x-axis. Geometric appeal, right? You just got to see that in your head. Yeah.
So those aren't spheres; those are like shells.
They're what now?
Those aren't like full spheres; they're just shells.
They're like bowls, kind of. Yeah, but these surfaces do not close up because hyperbolas don't. Right? Hyperbolas kind of extend asymptotically. Right? And so likewise, these you might say that these are asymptotic to a cone. Right? There's a I'm not going to try to draw, but it's like there's a cone coming out, in the x direction, and this surface kind of asymptotically approaches the cone. Does that make sense? Yeah. Yes.
So in this example, it's set equal to 1. What does that translate?
Oh, well, this is just this is the given of the question. I just picked an arbitrary equation.
But it's not above or below an axis. What does the 1 mean?
That's kind of what we're trying to figure out, right? We're trying to figure out what this thing looks like. And so the analysis, the argument that I'm making as we try to understand what does this equation represent, is that, well, first of all, it's rotationally symmetric. Second of all, this is what its cross-section looks like. And third, I can imagine rotating this cross-section to generate a surface.
So if it were equals 8,
then you're going to get you're going to have a different hyperbola. There'll be a slightly
because it would be x.
Because you see that whatever's here is going to translate down here, and so you're going to have to again remember all the high school algebra 2, and so you're going to have a different hyperbola to rotate, and you'll get a slightly different then result. Yeah. Okay, so here, and again, this is really hard to draw, and I'm sorry, but it's hard to draw. But let's be clear, I am not expecting y'all to become, Rembrandts of mathematical drawing, right? I know I'm not either. I do my best. This is a tough one, and so forgive yourself, right? But let's talk hypothetically. If you're on an exam and you want to get full credit for the question, right? Keep in mind, I've said this, a million times in the past. I'll say it another million times going forward. We're not interested in the result. We're interested in the reasoning, right? And so look at what I've got written down here. It is perfectly obvious that I'm arguing the rotational symmetry. It is perfectly obvious which plane I'm looking at a cross-section in. I get an equation. I've drawn what that looks like. I assert that I'm rotating around the x-axis. You can criticize this art all you want, and it deserves it, right? But my process is very clear, and this is full credit. Everybody see what I'm saying there? Don't get bogged down in the nitty-gritty details of beauty of drawing. It's not what we're here for, right? And we can't do it anyway. But make sure that how you concluded and how you generated your picture is evident in what you write. Okay. Next tool I want to give y'all. Really neat observation. Again, shows up a lot. This is a really powerful trick. That sometimes you're dealing with an equation that is a tweak of a different, nicer equation. Okay, so here, let's start with the nice one. I claim this is a really nice equation right there. That just says distance from the origin is 13. Cool, that's a sphere of radius 13. That's no problem. Boom. Right, and by the way, a fun little Pythagorean triple, this point right there, satisfies that equation. Wild. Right, everybody with me? Okay, now let's play a game. I ask what happens if everywhere in this nice equation that I started with, everywhere I had a z, I replace it with 2z. Like I did there. Now I changed the equation. Totally different equation. Well, different equation at this point. Okay? This little tweak that I did, replacing all the z's with 2z's, how does that change the picture? What does that do to the surface? Right? Yeah. So the idea is, let's think about what points would work, and will 3, 4, 12 that worked in this equation, will it work in this equation? No, clearly not. That 12 is going to get multiplied by 2. That's going to mess everything up, and it's crash and burn, and it just doesn't work, right? But you can see that coming. You can anticipate the 12 that I want to get squared in this term isn't going to get squared here because it gets multiplied by 2 first. So let's get clever, and let's put 6 there instead of 12. That 6 gets multiplied by 2 to make the 12 that gets squared, and all the arithmetic works out and then exactly as it did before. Right? So neat trick that whenever you do this move, whenever you replace all your z's with 2z, in effect, geometrically, what you're doing is effectively dividing all of the solution's z coordinates by 2. What had worked as a 12 now works as a 6. And it's like your surface, your whole surface, it gets just kind of compressed. I like to say squished. It's not fully smushed, right? But it gets kind of just squeezed down. All the z coordinates get cut in half. Yes?
Could you please repeat that process of replacing?
Repeat the what now?
The process where we replaced 2z with 6.
Yeah. So the point is, because in the algebra I replace z with 2z.
6 is 6z.
Well, effectively, if you replace the 12 with the 6, then effectively the arithmetic becomes morally the same arithmetic that it had been.
But if
Yeah.
we leave it as,
If you view it as like, you can
we use this as 12 and multiply 12 before we get a whole different thing.
Yeah. Then it just straight up doesn't work. Yeah, that's right. And so this point that had previously worked, right? That point is, well, it's like up here, and it just doesn't work anymore. Yeah. It doesn't satisfy the new equation. Yeah. Right. But when you put the 6 in, it does. So here's the big upshot then is this right here. When you do something to a variable in an equation, so what we did up there is we replaced all the z's with 2z's. When you do something to a variable in the equation consistently throughout the whole equation, the opposite happens to the surface. right? So here we multiplied the z by 2 in the equation, and then the z-coordinates of the solution got divided by 2. Surface got squished. So this is a broadly valid punchline. And so there's a couple of nice little examples here. And I like this one a lot. I'm gonna present this a little bit differently. Let's come at this from the point of view of, suppose we start by being asked this question. How would I understand what this surface looks like? And I don't know. Maybe a rotation. Maybe is this rotationally symmetric? Can I make a rotation argument? No, the A and the B are probably different. X and Y do not appear only in the special form, and if you try to maneuver things around where it actually would look like that, no, you're going to fail. You can't. It just doesn't work. Likewise with the Y and the Z, likewise with the X and the Z. This is not rotationally symmetric around anything. Okay, but what I can do is say, hey, you know what? That looks a lot like this. This is a unit sphere, no problem, because this is just saying distance to the origin is 1, right? So super easy to understand here, and this is not that different. And I can show you exactly how to tweak it. Everywhere I see an X, I replace it with X over A. Right? Every X in this original equation, I just replace with X divided by A, and that then is going to stretch by a factor of A in the X direction. And then likewise for the others, Y gets replaced by Y over B. That's going to stretch by a factor of B in the Y direction, and Z gets replaced by Z over C, and that stretches by a factor of C in the Z direction. So, yeah. So the really nice, what I think is really nice about this, we took something where we have no rotational foot in the door, we related it to something that does. We did business. We did most of the heavy lifting of this question in the context of this easier question where we've got rotational symmetry arguments and distance arguments, and this is just easy, right? And then we keep track of how did we tweak it algebraically and what are the resulting consequences geometrically, and that actually allows us to conclude what this surface looks like. Whereas we had no other, like initially, without this sort of relating it back to the green surface, we had no foot in the door on it. Yes?
So this one wouldn't pass the vertical line test?
Correct. Yeah, that's right. This surface is not a graph of anything because you can't solve uniquely for X, Y, or Z because you'll always get kind of two answers because of the plus minus.
Okay, so
yes.
What are you using this for?
Well, just keep in mind, graph is just some construction, right? The fact that this isn't a graph of anything is a true, but it's one of many true facts, right? But it's not what we're interested in. Yeah, what we're interested in here is this equation came to us, and we just need to know what it looks like.
Okay.
Yeah, and so this is how we can decide what this surface looks like by relating it to something that we already knew the answer. Yeah. So real quick, I know we're out of time. This is just other examples. These are morally equivalent. Please give these a look. Please be careful about, don't interpret this as dividing by a squared. You're dividing by a, not a squared. Think through the algebra. Make sure you're comfortable with that, right? And everything else is pretty much the same. Okay, we're done with section 2.1, finally. See y'all on Friday. Have a good one.
I have a quick question.
Yeah, give me just 1 second to get the recording stopped here.